Algebra 2 students, in this video we will be studying inverse relationships, okay? Inverse relationships. Now we're going to do this by looking at the inverses of ordered pairs, graphs, and functions, okay? So here we go. Your heading for today is inverse relationships. Please write that down. Lesson 6.3, please write that down and be sure to include today's date. Okay? Inverse relationships, lesson 6.3. And be sure to include today's date. Now, first, let me explain what an inverse relationship is. Okay? Let me explain what I'm talking about. Simply put, and I would copy this down if I were you, it is when the given x and y values of a given relationship are swapped. Okay, let me show you what I mean. Simply put, an inverse relationship is when the x and y values are swapped. So your y values become your x values, and your x values become your y values. Okay, let me show you what I mean. Write down these 5 ordered pairs, please. Write down these 5 ordered pairs. Now I'm going to keep going. If you need to pause the video, that's fine. But if I asked you to write the inverse ordered pairs of these given ordered pairs, here's what you would write. Now this is really, really difficult, so please pay close attention, okay? And yes, I'm being sarcastic. See these two values, x and y, swap them. So the -3 comes first and the 0 comes second. Next ordered pair, swap them. So the -1 comes first and the 1 comes second. Next, I'll put little check marks here. Next ordered pair, swap those. 1 comes first and the 2 comes second. Next ordered pair, swap those. Of course, they're both 3, so it really doesn't matter. And then swap this last ordered pair, 5, 4. There you go, it's that simple, okay? Now, inverse relationships can be a little more complex, especially when you get into word problems and functions. And we're going to get into that, but for now, let's keep it simple. When I say we have an inverse relationship, it's when the x and y values are swapped, okay? Now, do you see what I did? I simply swapped the x and y values. So, because I did this, these two sets of ordered pairs right here, this set and this set, those two sets of ordered pairs are inverses of each other. Or we can say they have an inverse relationship. Alright, now, I know it's really easy, but just to make sure we're all on the same page, go ahead and do this one on your own. So I'm going to go ahead and put the answer down here. So if you want to pause the video, do it, and then restart the video, that's fine. It's really simple. But go ahead and copy this in your notes right here. And then in your notes, write down inverse ordered pairs, and then write the answer. Okay? So I want you to find the inverse ordered pairs of these given ordered pairs. Alright? I'm going to go ahead and start now, so pause the video, do that, and then restart the video. And there's the answer. I just simply took all of my x's and my y's and I swapped places with them. Very simple, okay? In every ordered pair. Now, what if I gave you a graph and I asked you to find the inverse graph? Since I just showed you how to find the inverse of a given set of ordered pairs, it really shouldn't be that difficult if you'll think about it, okay? Let's try one. Please copy this in your notes the best that you can. I'm going to highlight some points for you here. Make sure you get that ordered pair on your graph. And we're going to say it crosses the x-axis right there, even though it doesn't quite do that. And we're going to use this ordered pair and this ordered pair right here. Okay, so as as you write this, as you copy this in your notes, make sure those four ordered pairs are highlighted, okay? I'm going to change colors to black, or to black. I'll use blue. And I'm going to find the inverse of this graph. So I'm going to move on. If you've not copied this yet, pause the video and copy this down. And then we're going to find the inverse graph of this given graph. Now this ordered pair here is -6, 5. This one here is -3, 3. This ordered pair is 2, 0. And this ordered pair is 5, -2. So the inverse graph of this given red graph has these ordered pairs, only they're swapped. So instead of -6, 5, I'm going to use 5, -6. So over 5, down -6. Instead of using -3, 3, I'm going to use 3, -3. So over 3, down 3. Instead of using 2, 0, I'm going to use 0, 2. So 0, 2. And instead of using 5, -2, I'm going to use -2, 5. And there we go. I have the inverse graph, so we'll quickly get that up here. The best that we can. And there we go. Now, pretty simple, okay? Now, Mr. Earhart, you just chose these 4 points. Look, students, you are more than welcome to work your way along the x-axis. For example, here we're at -6, okay? Here we're at -5. So this ordered pair right here would be -5, comma, 1, 2, 3, 4, about 4.2. So -5, comma, 4.2. That's fine. And then work your way along to the -4 right here. So go straight up. This ordered pair right here would be -4, comma, 1, 2, 3, about 3.8. The reason I didn't use those points is because they have decimals. You are more than welcome to use as many ordered pairs as you want to. Okay, that's totally fine. Make sure you use enough ordered pairs to get a good picture of the graph. Okay? Now, look. I want to show you something now that's going to be really confusing. You do not need to understand this, but listen carefully anyways. I want to show you something else about inverse graphs that are always true. Okay? Would you please watch this? I'm going to draw a line that goes through 1, 1, 2, 2, 3, 3, 4, 4, 5, 5, 6, 6, 7, 7, 0, 0, -1, -1, -2, -2, -3, -3. You get the point. Now there's that line. In mathematics, we call that line y equals x. Okay? If you were to graph y equals x, you would get this line here, and here's what I want to show you. Please watch this. Notice this ordered pair here. If I were to draw a line from the blue dot to the green line so that it's perpendicular and continue it, this blue point is the same distance from the green line as this point. See this black point here? If I drew a line that's perfectly perpendicular to the green line, okay? And actually, I've got to be careful here. This should work unless I made a mistake. Yeah, I see what I did. It's really hard, guys, to draw a perfectly perpendicular line. It really is. But this point theoretically should connect to that point. There we go. Looks pretty good, actually. If I do say so myself. Just kidding. But look. There we go. Now look. This black line really does look perpendicular to the green line. And the distance from this point to the green line is the same as from the green line to this point. Now I'll do it one more time, and then I'll quit boring you guys to death, okay? Let's take a look at one more. We're going to go from this point here to this point over here. equals x. And remember, we learned this in geometry last year. When a point is equidistant from the line, that means it's perpendicular. Because guys, if I have a point and a line, and I say how far is that point from the line, there's a lot of distances. We learned last year the distance from a point to a line is always the perpendicular distance. So this point and this point here, this point and this point, they're equidistant from the green line. Okay? And so are the other points. So that's all I wanted to show you about that. But the main thing I want you to be able to do is to be able to take a given graph. Okay, like I did, I gave you the red graph, and I want you to be able to draw or graph the inverse of it. Okay, let's try another one. Take some really good notes. Actually, let's stop and review. So to write the inverse of the red graph, I found some ordered points on the graph. Then I reversed those ordered pairs, plotted them, and drew the inverse graph. And I'm sorry, guys, but there's something else I have to tell you. So would you please listen to me carefully? It's very important that you understand this. You're going to need to take a bunch of side notes on this. Let's take a look at the red graph first. This is something I've never taught you, okay? If you ever want to know if a graph is a function, remember how we learned every input has to have exactly one output? Do you remember that? You should, okay? Well, there's another way to test a graph. It's called the vertical line test. Would you please write that in your notes? The vertical line test. You need to know this. And if I asked you, hey students, is this red graph, does it represent a function? You look, is there anywhere that you can draw a vertical line, anywhere, in which the vertical line crosses the red graph in more than one place? And the answer is no. Now some of those lines aren't vertical, but you understand. If there's one place, or more than one place for that matter, if there's any places at all, just one, that you draw a vertical line and it crosses the red graph in more than one place, then it's not a function. But as you look at this red line, you know every single vertical line that I draw only intersects the red line in one place, okay? So, the red line is a function because it passed the vertical line test. Now, does the blue graph represent a function? Well, sure it does. I don't care where you draw your vertical lines. I don't care if you draw a million of them. Any vertical line that you draw on the blue graph will cross the blue graph in only one place, right? Think about it. Is there anywhere at all, if there's just one place or more that you can draw a vertical line and it intersects the blue graph in more than one place, then it's not a function. So, is this blue graph a function? Does it represent a function? Yes, it does, definitely, because it passed the vertical line test. Now, I have another question for you. Are you ready for this? Let's say I gave you that red graph like that, and I said to you, hey students, does that red graph represent a function? You would say, yes, Mr. Earhart, the vertical line test passes everywhere we draw a vertical line. It only crosses the graph in one place, fine. But then what if I asked you this? What if I said, does the inverse of this graph, does the inverse of this graph represent a function? Now you say, well, Mr. Earhart, that's stupid. We just had the blue graph up here. We know it does. But pretend that you didn't. Pretend that I'm not going to allow you to draw the blue graph. Pretend I'm not going to allow you to draw the inverse graph. I just want you to look at this graph here and then tell me yes or no. The inverse of this graph does or does not represent a function. Well, guys, think about it. Are you ready for this? How could I do that? We'll use common sense, okay? swap the x and the y values, correct? So would it not make sense if we're going to test this red line, not to see if the red line is a function, but to see if its inverse is a function? Would it not make sense we would swap the line, and instead of using a vertical line test, we would use a horizontal line test? Does that make sense? Sure it does, guys. So, are you listening to me? If you will listen to me, I will explain this well. If I said to you, does this red graph represent a function? You would use the vertical line test, no problem. But if I said to you, does the inverse of this given graph represent a function? And I did not allow you to write the inverse graph, you would use the horizontal line test. So, is there anywhere in this graph, anywhere, that you can draw a horizontal line in such a way that it crosses the graph in more than one place? No. Any horizontal line that you draw is going to cross the graph in more than one place. So, does the inverse of this graph represent a function? Yes, it does, because the horizontal line test passed. So yes. Now, we already knew the inverse was a function because we already saw it. Remember, it's the blue line that looked like what it looked like, guys. Something like this, I think, whatever it was. I forget. But we already tested it and we knew that it was an inverse, that it was a function. Excuse me. But what if you had not seen the graph? How could you know for sure? Use the horizontal line test. We're going to go over all this again right now in this next problem, so let's jump on to another one. Now, you might want to pause the video, okay, and copy this down. We're going to try to find the inverse of this graph here. So go ahead and I'm going to move on. So if I were you, I would pause the video and then copy this down, then don't work ahead, okay? Now, we're going to do this one a little backwards, okay? First of all, I'm going to come over here and put this. I'm going to put red graph, okay? Is it a function? Well, let's use the vertical line test. Let's find out. You ready? Is there anywhere you can draw a vertical line in such a way that it crosses the graph in more than one place? No. No way. Every vertical line you draw crosses the graph in only one place. So it passes the vertical line test of the red graph that you see in front of you. Yes. It is a function. Got it? Now, before we find the inverse and put it up here, and by the way, are you listening? When we do that, we're going to use blue. Okay? So I'm going to go ahead and call it the blue inverse graph. Okay? When we graph in just a minute the inverse graph, will it be a function? Remember what I just taught you. If you're checking to see if the inverse graph has a function, use the horizontal line test. So here we go. Let's use the horizontal line test on this graph. Is there anywhere you can draw a horizontal line that crosses the graph in more than one place? Booyah, right there. It crosses the graph here and here. It only has to fail once to fail. So, the blue inverse graph is not going to be a function. Now let's see if that's true. Let's go ahead and find the function. Let's see if that's true, okay? Here we go. Let's use the blue graph. Okay, this ordered pair here is about negative 3.5, and it's up about 3. So negative 3.5. 3. So we're going to swap that and we're going to go over 3, negative 3.5. So there we go. Alright, let's try another point. We'll kind of slide down to here. Okay, this point here is negative 3, 1. Negative 3, 1. So we're going to use 1, negative 3. Alright, let's jump onto the vertex here. The vertex looks like it's about negative 1/2. And it's down negative 1 over half down 1. So we're going to use negative negative 1 half. So negative 1, negative 1 half. So about right there. Alright? Now students, to be consistent, we kind of used a point to see. We used a point here, and we used a point here, and then we used the red point here, those 3 points. And I should not have done those in blue. That's going to be confusing. We used this point here, and we swapped it. We used this point here, and this point here. So let's be consistent. Let's jump over now. It looks like it's close enough, equal at this point. It's close enough to being right there. So we're going to call this ordered pair right here over 2 and up 1. So then the inverse, swap those two. The inverse would be over 1 up 2. Okay? Now, we used this ordered pair here, so let's come straight across, and we'll use this one about right here. Would be good. Alright? Actually, that's not correct. We used, this point was actually right there, and I apologize, but that's the point we used. So, then we're going to use this point, and it's off a little bit. I just kind of sketched it. We'll keep it consistent. We'll say it's about right there, which would be, and again, the graphs on your test and out of your book will be nice, pretty graphs. My parabola here is really bad, but it would be over about 2 and a half and up 3. So you're over 2 and a half. Do you see it okay? 1, 2 and a half, up 3. So swap those two, and you'll get 3, 2 and a half. So there's your blue point. So it looks like we're getting a sideways parabola. Do you see it okay? Alright. Now, there we go. I did it. Now, first of all, I'm not going to get all technical on you, but remember I told you, if I were to draw a line, the y equals x line, like this. Remember I told you this in the last graph, and I'm not going to make you know this, but again, all of these points would be, these 2 points here would be equidistant from the green line. These 2 points are equidistant from the green line. These 2 points right here, equidistant from the green line. These 2 points here would be equidistant from the green line. Okay, but again, I'm just throwing that in there just to make you think. Okay, you don't have to know that now. First of all, I have accomplished my goal. I took the red given graph and I drew the inverse graph. Okay, now, what was my prediction? What was my prediction of the blue graph? I said it was what? Not a function. Let's see if I'm right. If this red function was not here and all that I gave it is blue function, I said, hey, is that blue function, graph, if I did not give you this red graph and all that I gave you was this blue graph, and I said to you, hey, is that blue graph a function, you would run the vertical line test, and it would fail. So, the blue graph is not a function. Now, how was I able to make that prediction before the glue? How was I able to make that prediction before the blue graph was even up here? I was able to make that prediction because, remember, I used the horizontal line test. Remember, I used the horizontal line test on the red graph, right? Sure I did. I looked at that red graph and I drew horizontal lines, and I saw right away that the horizontal line touched the graph in more than one place. So then I knew after I graphed the blue graph, it would not be a function, and it wasn't. After I graphed it, I did the horizontal line test, and you saw, or the vertical line test, and you saw it was not a function. Okay? Hope that makes sense. Let's move on. Now, let's learn how to find the inverse of. Now, so far we've learned how to find the inverse of ordered pairs. We've learned how to find the inverse of a given graph. Now we're going to find the inverse of a given equation or function. Okay? So here we go. Let's find the inverse of this equation. Please copy this down. Let's find the inverse of this equation. Are you ready? It's really, really, really easy. Everywhere there's a y, you put an x. And everywhere there's an x, you put a y. Now guys, it doesn't get any easy, okay? So if I'm going to get y by itself, bring the negative 3 over and make it a positive 3. So now I have x positive 3 equals 2y. And now, if I want to get y by itself, I divide everything by 2. Now don't forget there's a 1 right here, okay? So you're welcome to put x over 2. I have no problem with that. Personally, for me, I'm going to put 1 half x because there is a 1 here. That's how I like to do it, okay? Now it's a positive over a positive, so the whole fraction is positive. Here we have a positive over a positive, so the whole fraction becomes positive. And then over here your 2's cancel. And there you go. You're finished. This equation here is the inverse of this equation here. Now, isn't that simple? Everywhere there's an x, you put a what? A y. And everywhere there's a y, you put a what? An x. And then you get y by itself. Now, I'm not sure if the back of your book requires you to get y by itself. In other words, this book might just say, swap the x's and y's like I did here. This y became an x, and this x became a y, and then you're finished. I don't like that. I'm not going to allow that. A good solid math book then wants you to get y by itself. So if the answers in the back of the book look like this, ignore that. I do want you on tests and quizzes to get y by itself. So, step 1, if I give you an equation and I tell you to find the inverse of that equation. Step 1, everywhere there's an x, you put a y. Everywhere there's a y, you put an x. And then you take that equation and get y by itself. That's pretty simple, students, is it not? It really, really is. Okay, moving on. Now, let's say that I gave you a function, okay? A function. Let's find the inverse of this given function. So there it is. Would you please copy that in your notes? I'm going to bring it over here. F of x equals 3x minus 1. I want you to find the inverse of that function. Now, we don't do this all the time, but it's totally okay to do. As long as you remember you do have f of x here, okay? But it's okay to put a y here for f of x just for a little bit, okay? If that helps you, I have no problem with that. A lot of students do that, and that's fine. As long as you remember your original problem was a function of x. So for f of x, I'm going to go ahead and put a y. That helps a little bit, okay? And now we're all set. You know what to do, don't you? Let's find the inverse. Everywhere there's a y, we're going to put a what? X. Everywhere there's an x, we're going to put a what? A y. Is that easy? Now, let's get y by itself. Bring the negative 1 over and make it a positive 1. Now divide everything by 3. Divide by 3. Divide by 3. Divide by 3. If you want to put x over 3 down here, I have no problem with that. Please feel free to do that, okay? I will not take any points off from me. I have a 1 here, so I like to put 1/3 x. And then here I have another 1/3. And then over here my 3's cancel, leaving me with y. Now, I had a positive over a positive, so the whole fraction is positive. I have a positive over a positive, so this whole fraction is positive. And it equals y. Now in the last problem, are you paying attention, students? Watch this. In the last problem, my original problem was not written in functional notation. So my answer like this was fine. However, in this problem, your original problem was written in functional notation. So when you come down here to write your inverse, here's how you must write it. I'll explain this in a second. F with a little negative 1 and then x equals 1/3 x plus 1/3. Now, every year I teach this, and every year students forget this, and that's not my fault. I'm telling you now, if the original problem is not written in functional notation, then your inverse answer does not need to be written in functional notation. However, if your original problem is written in functional notation, f of x or g of x or h of x, whatever, then your inverse answer must be written in functional notation. Now, I don't want you to look dumb when you get to college. You do not read this f to the negative 1 power of x. That is not what this means. It means f inverse of x. That's how you read this. F inverse of x equals 1/3 x plus 1/3. So you read this f inverse of x. Now, if this original problem right here would have been g of x, then your answer down here would be g negative 1, g inverse of x. It all comes down to what your original problem was written as, okay? Here your original problem was written f of x, so your answer must be written f inverse of x. So there's your final answer. The only reason I put this y in right here for f of x was just to make the problem a little easier. Then once I get y all by itself down here, you have to get rid of this and you have to put f inverse of x, okay? So these two functions right here are inverses of each other. If that doesn't make sense, go back and watch it again, okay? You've got to understand that, okay? Alright, moving on. Now, I want to show you another relationship between two functions that you really need to see, okay? So I need you to pay close attention. Here we go. Now, let me go back and copy something here. Just to save me some time here. Okay, now the last problem we did, we started off with this function here, right? Didn't we? I'm sure we did. And we ended up with this function right here, this inverse function, correct? I'll just go ahead and copy it so I'm not going to waste a bunch of time. There we go. Now, I want to show you one more relationship and then we're finally done with this video. Okay, so here it is. Excuse me. Now, let me show you something here. Are you ready? In your notes, I want you to write down the composition f of f inverse of x. Okay? Then come over here and write f inverse of f of x. Okay? There we go. Remember this composition. We're going to find the composition both ways. F of f inverse of x and f inverse of f of x. Do you see the difference? Here we have this, and then they're swapped over here. We're going to find the composition, and you must do it both ways. Why, Mr. Earhart? You're going to see in a second. Watch what happens, okay? So, let's start off with this one right here. What letter's on the outside? F. So you write your f function right here, remember? Now, everywhere there's an x, you put a big parentheses. Okay? Now, what's the next letter? F inverse. So you come over here and get your f inverse, and you put it over here. Now simplify this expression and watch what happens. The first thing you do is you multiply your 3 through. 3 times 1/3 x is 1x. 3 times 1/3 is 1. Then bring down your negative 1. Now, we have two constant terms. Combine those and they cancel out, right? Positive 1, negative 1, they cancel out, leaving you with 1x, or really just what? X. Now let's come over here. We'll come back to this in a second. Let's come over here. Over here we're going to do f inverse of f of x. So what's my first letter on the outside? F inverse. So I take this function here and I x, I put a parentheses. So 1/3, put a parentheses for x, then positive 1/3. Now, what's my next letter? F. So pick up your f function and put it over here. And here we go. Take your 1/3 and multiply it through. 1/3 times 3x is 1x. Use a calculator if you need to. 1/3 times 3 is 1. 1/3 times -1 is -1/3. Then bring down your positive 1/3. Here's your two constant terms. Notice they happen to cancel out, -1/3 and positive 1/3. So you're left with 1x, or really just x. Okay, here's the relationship I want you to learn. If two functions are truly what? Inverses of each other. Are truly inverses of each other. Then you can take the composition both ways and you will get out x both times. If you do not get out x both times, then these two functions are not inverses of each other. You're not going to get out -x. You're not going to get out x plus 1. You're going to get out x and x. And it must happen to both of these. If you get out x here and over here you get out x plus 3, then these two functions are not inverses of each other. So I'm showing you this because it's a neat way to test whether two functions are truly inverses of each other. Okay? Do you understand? You can take the composition going both ways, and after you're all done simplifying, you will get out an x and an x, unless you made a mistake somewhere. Okay? That's the other relationship I wanted to show you. Now, I don't feel like the math we covered is really that difficult. It's just a lot of little stuff. So I want to quickly review what I expect you to be able to do. I expect you to be given sets of ordered pairs, and you write the inverse of these ordered pairs. We did that earlier in the video. I expect you to be able to take a graph and do two things. Predict whether the inverse graph is a what? Function. And how do you do that? Horizontal line test. And I expect you to be able to find the inverse graph of a given graph. So you find some ordered pairs, swap them, plot them, and draw the graph. I expect you to be able to take an equation or a function and find the inverse function or equation. And don't forget to use the proper notation if the original problem was written in functional notation. And then lastly, I expect you to be able to take two functions and prove that they are inverses of each other by using composition of functions both ways. Okay? Alright, that's it. Guys, I hope this video has been a help to you. If you have any questions, never hesitate